Alrighty, we're back with chapter 6. We're going to do the second section here, and what we're going to be talking about is basically the Reynolds transport theorem applied to momentum, and how we think of that. We'll express the Reynolds transport theorem, and we're going to do two things. We're going to look at what we mean by the terms momentum flow and momentum accumulation. These are terms that fall out of the Reynolds transport theorem and are very, very similar to mass flow and mass accumulation in the Reynolds transport theorem applied to mass, or the continuity equation. So let's get started. I'm just going to zip ahead to section 2 here. And the first thing, that if you remember, this is where we left off with section 1, where we talked about how the sum of the forces of the external forces are equal to the time rate of change in the momentum in a closed system. So let's talk about how that applies to the Reynolds transport theorem now. When we're interested in momentum, the momentum equation, what is the extensive property? Well, that's pretty obvious. Our interested extensive property is the momentum, mass times velocity. So there it is. Momentum is B. That's capital B in our Reynolds transport theorem applied to momentum. Now, what is the intensive property? If our extensive property, you remember B is our extensive property, little b was just B over M. And so in the case of momentum, our intensive property is going to be just the velocity. So that's so here we have momentum, and down here we're going to have velocity as being our extensive property right here. So extensive and intensive. And so we can just merely write down the equation as we did before. Now, instead of having 1 here, as we did before, because if you remember, our intensive property for mass was just 1, mass over mass was 1, so we didn't have a term here. But this time, what we have over here is the rate of change of momentum in a closed system, and we just saw from section 1 that that's equal to the sum of the external forces. That's going to be equal to the time rate of change of now V, the intensive property, times rho d volume through the time rate of change of that. This is going to be our momentum accumulation, basically, in the control volume. And over here we have, again, the control surface, the rate of momentum flow through a control surface. So now, instead of just having a 1 here and just having rho v dA, we actually have an extra velocity multiplying by here. This is the fluid velocity, and this is the particle velocity. So, so we can write this in a couple of different ways again, just similarly to what we did with the continuity equation, and this is what we get for the general form of the momentum equation. The sum of the external forces, which is equal to d momentum dt in a closed system, the sum of the external forces is going to equal the time rate of change of this quantity plus this quantity crossing the control surface. In simplified form, this is the way it looks. This can be written as the time rate of change of the momentum in the control volume times the volume, the velocity in the control volume, minus the outflow through the any control surfaces we might have, minus the inflow of momentum. So note that actually this is actually not a momentum. It's a momentum flow, or a momentum rate. So this is m dot. So it's dm dt, and same with this. So these are flows or rates of change of momentum across control surfaces. So here's a conceptual picture similar to what we had for the continuity equation. We have our general equation, which we just talked about, our simplified version, which we just talked about. But then the main ideas, these two things are really important. What does it mean? And so we have a good idea of what the left-hand side is. These are the sum of the forces acting on the matter that's inside the control volume. So we're taking all the external forces and we're summing them up and looking at how they affect what's inside the control volume. That's going to be our net force. These concept of momentum accumulation and net momentum flow are now new concepts, I believe. And so the second term is really the time rate of change of the momentum of the matter inside the control volume. This is going to be momentum accumulation if we're accumulating momentum within the control volume, or if we're losing it, and if it's changing, if the momentum of the mass inside the control volume is changing, or if the momentum is changing. And then secondly, the outflow of momentum and the inflow of momentum is really going to be the net rate at which fluid flow transports momentum out of the control volume through the control surfaces. So that's going to be the net momentum outflow, actually, since it's outflow minus inflow. So the main thing that we want to do is find out what we mean by, these two new terms, momentum flow and momentum accumulation. So let's take momentum flow first. So what's the physical interpretation of these terms? We're talking about the far right term first. So if we look at a particle here and we watch it cross this dashed line here, it might be a control surface, this vertical dashed line here, and we're going to watch a fluid particle go through that. And if we track it for a certain amount of time, the length of that particle is going to be just the velocity times the time. Remember that velocity is in meters per second, and for instance, and time is in seconds. So this gives us a length. And so we know the length of that fluid parcel, and if we know the area of it, if we just assume it's just this circular area here, we just get this cylinder of fluid that's passing across this control surface. And we can write its volume now quite easily as being L, which is the length, times the little delta area of the end here for the cylinder. So the cylinder is just the area, the volume of a cylinder is just the area times the length. But we can also substitute for L, we can substitute in V delta T, and so this becomes our volume. So when we want to express the amount of momentum flow, we write that as basically if we want to write the momentum, we have to write m times v. And so what we have here is the mass. The mass is equal to the density times the volume. But of course, in this case, our volume is equal to rho v delta t, that was our L, delta A. So this turns out to be our mass here. And so this term right here is just mass. So that gives us, if we sum all the mass going through the control surface, that's at any time, that's going to give us the momentum. But really what we're interested in the Reynolds transport theorem is the change of that in time. So we look at how we take the momentum of all the particles crossing the control surface and divide it by time. And so what we end up with over here is really rho v times v again times the delta area. We basically divided both sides of the equation by delta t. This delta t has canceled out, or you can think of it as having been put to the other side. So this is now really momentum over time, because this time has been divided back out over to the other side. And we're left with just rho times velocity again times dA. Note that in general, only this one here actually is a vector, and that's going to be that's going to tell us something about the fluid direction. So here's an example of what we mean by momentum flow. We have a a fluid jet striking, this is the jet of fluid that's striking what's called a vein here. And we've got this momentum coming in and we have this momentum coming out. And just a quick glance at the magnitudes, we can see that this is equal to 16 and this is equal to 16 just by taking 8 times 2. And that's going to be in kilogram meter second squared, over second squared in both cases. So we're not really changing the magnitude of the momentum going in here and coming out the other side of the vein after it strikes this. We haven't changed the amount of momentum going in or out, but we've certainly changed the direction. And of course, momentum has direction through its velocity. So what we have, as we can see in the book, we have to write down, if we were interested in writing down this, let me go back and show you this term. If we're interested in writing this term in the Reynolds transport theorem for momentum, then we have to concentrate on the outflow first minus the inflow. So this, let me get my pencil, this is basically this term here, m dot v2. You can see that v2 is directed, this is v2 right here, it's directed down and towards the right of the slide here, whereas v1 up here is just directed in the x direction. So we've got this being the momentum in the rate of momentum from this term, and that's being subtracted. This is out minus in. And again, note that the rate of momentum, so dmv dt, is equal to a force. The units are equal to a force. It's kilogram a meter over second squared, which are units of newtons. So these answers come out in newtons. So the input is coming in the x direction only here, and the outflow is coming, it's being separated into an x and a y component. So that's what we mean by momentum flow. Momentum flow is really just the force that's impinging, going through this control surface at this point, and then the force, the directional force that's coming out in this direction. But of course we do need to maintain our vectors, because vectors through their acceleration basically and the rate of change in velocity have direction. All right, what do we mean by momentum accumulation? This would be the middle term in the equation. If we go back here, we're talking now about this term, the momentum accumulation. And if I just skip back for just a second, remember that's the time rate of change of the momentum of matter inside the control volume. Momentum accumulation, kind of a new term. So here it is. Momentum accumulation is going to be, if we're considering a fluid, a piece of volume, small volume inside our control volume. Our control volume is given by whatever's contained within this control surface. So that that momentum is just going to be this mass times mass times velocity, and we're going to write the mass as just the density divided by this delta volume unit. It's a small piece of volume within the larger control volume. So that's what our momentum is going to be, and simply if we write down the total momentum inside the control volume, we just need to sum this over the control volume. And in fact, I think maybe the book ought to have a little CV here to designate that we're adding up each one of these little delta volumes that's within this larger control volume here. So we sum up all the different pieces of volume, multiply them times the density and times the velocity, and that's going to give us, if we sum them all up, that's going to give us the total momentum. And really what we're interested in when we get the momentum accumulation is the rate of change of that total momentum inside the control volume. So we take the time derivative of that. So you can see we just take this down here and take the time derivative of it, and that gives us that middle term. Now, for a lot of problems, the book mentions that for a lot of problems, this term will be 0. Imagine that you've got a steady flow coming in here, and you've got this, a steady flow of fluid coming in here and a steady flow of fluid coming out here. Since you're not changing the rate at which things are going in or out, how can the momentum be accumulating it inside the control volume? And especially if the velocity is constant along streamlines in here, if the velocity isn't changing with respect to time, we're not going to get any forces. So you can't be accumulating there. It's going to be a pretty rare situation where we're going to be accumulating momentum. So a lot of times this term is equal to 0. I wouldn't say always, but oops, I should probably not write not equal to 0. I should probably write equal to 0. A lot of times that'll be equal to 0, or maybe in some cases close to 0. And the book mentions that you should analyze your situation and carefully consider this term, but a lot of times we'll be able to neglect it. And that's it for section 6.2. I'll just draw your attention to where we'll start with 6.3, which is a summary of the linear momentum equation. And it's very similar to the continuity equation. We have the general form and the simplified form. And we have over here a list of all the different variables. But we should now have a good feeling for what we mean by the momentum flow. This is really the forces of the fluid acting through the control surfaces. Remember, it's the rate of change of momentum. And we also have the term here, which is the momentum accumulation. And over on the left-hand side, the sum of the external forces. Okay, thank you.